Okay. So this is a Zoom meeting for Physics 231C. We're finishing the second week of classes. We've already completed chapter 1 last week, and I guess the beginning of this week. And now we're working on chapter 2. And Friday afternoon at 4 o'clock will be our normal Zoom meeting time. Now I'm recording the meeting. Yeah, it's recording. So we're working on chapter 2. There's reading quiz 1, which is the reading quiz for chapter 2, and that's due at the end of today. Most people have already finished it. And then there's problem set 1. That's the long set of homework problems from chapter 2. And that's due at the end of Monday next week. Now, when you read the chapter, you should take notes. So here, for example, would be a set of notes for chapter 2, but these aren't really complete. I mean, you want to have a complete set of important equations. You don't want to write down every equation. That would be too much. You want to write down all the important equations. So for each section in a chapter, there might be three equations that are important for that section. So, I would say that reading a chapter in this book should take about 3 hours. You don't have to do it all at the same time. You can spread it out over a few days. And it should produce about 2 pages of notes. Well, 1 page of notes front and back. This chapter is on kinematics. Kinematics is the mathematics that describes motion. And chapter 2 is kinematics for one dimension. That is to say, for an object moving along a line. Now, that doesn't sound very interesting, just moving along a line. In chapter 3, we'll be moving in 2 dimensions. But actually, even moving in 1 dimension has some interesting aspects. You have to have a mathematical method for describing the position of the particle as a function of time. And we'll treat the line on which the object is moving, we'll treat that as a number line. And so the position on the line is a number, corresponds to a number on the number line. And that number is called the coordinate. So for motion in 1 dimension, we have position, or we also call that coordinate, which is the x value, the numerical value along the number line. And that will depend on time. So x is a function of time. Then there's velocity. Velocity is the rate of change of position. So as the position of the particle changes along the line, it will have a velocity. And velocity is the change in position divided by the change in time. That is the change in coordinate value divided by the time during which that motion occurred. Now, any quantity, any mathematical quantity should have a unit of measurement. So as we saw last week, the standard unit of measurement for position is meters. The position is the distance from the 0 point on the number line. That can either be positive or negative. And that has to be measured in some unit of length. And a standard unit of standard units is a meter. So the unit of position will be meters. That's the standard unit. But it can be some other unit. It could be centimeters, or it could be millimeters, or it could be miles or inches. But the standard unit is a meter. Now, the standard unit of velocity will be, I have here in the numerator meters, in the denominator seconds, so it'll be meters divided by seconds. It's the rate of change of the coordinate. Now, we may also have acceleration. Acceleration is the rate of change of velocity. So what's the unit of acceleration? Well, the numerator here is meters per second. The denominator here is seconds. So it'll be meters per second, or I can write that usually as meters per second squared. It's a change of the number of meters per second divided by the number of seconds. So it's meters per second squared. Now, even one-dimensional motion is interesting because there can be acceleration. And in particular, the simplest case is constant acceleration. So we have special equations that apply when the acceleration is constant, that you must never use if the acceleration is not constant. But in a lot of the problems for this week, the acceleration is constant. So you can use these units. The position as a function of time is a constant x0 plus a constant v0 times t plus 1/2 the acceleration times t squared. And it was the great Galileo Galilei who determined that when there's constant acceleration, the position changes as the square of the time. Now, the velocity is a constant v0 plus the acceleration times the time. So the velocity is just increasing linearly as a function of time, and the rate of change is the acceleration a, if a is constant. And of course, the acceleration itself is a, which for constant acceleration doesn't depend on time. There's one other equation for constant acceleration that's often useful. This relates position as a function of time. This relates velocity as a function of time. There's a relation between velocity as a function of position when an object is accelerating. And that equation is delta v squared is 2a times delta x, where we use this delta notation, which I talked about a little bit last time. We'll often use the delta notation. Now, when you use a capital delta, that means that it can be any size. It doesn't have to be particularly small. But when I use a little delta, a lowercase delta, that implies that the change is very small. So here, delta t, the time over which the velocity is written is a very small time interval, maybe a millisecond. And delta x is the very small change in coordinate that occurs during that millisecond. So delta x is very small, delta t is very small, but the velocity is the ratio of two small numbers. Well, that can either be large or small or intermediate. We write this as the instantaneous velocity because we take delta t to be very small. That's a very small time interval. Well, right at the center of that time interval, let's say, is the time t, and this is the instantaneous velocity. And similarly here, instantaneous acceleration. And these are instantaneous position, velocity, and acceleration at one particular point in time. These constants x0 and v0 depend on the value of position and time at some initial time. So these equations are valid where the initial time is 0. So these equations are valid where t0, the initial time, the time where you start observing the motion, is assumed to be 0. Then x0 is the initial position, because if I set t equals 0, these two terms would be 0, and I would just have x at time 0 is x0, the initial position. Similarly, v at time 0 is the initial velocity. All right, so in the future, we'll also consider problems where the acceleration is not constant. And then we can't use these equations. A very good example of a case with constant acceleration is free fall in Earth's gravity. So here's the example, a falling object. You have, in this case, the one dimension is vertical. So we could set up a number line from some ground level, that would be the origin, upward. And the initial position might be some height. Suppose you drop an object from some height h with no velocity. Well, gravity will pull it down to the ground, so it'll fall to the ground. We're again taking t equals 0 to be the initial time. That's when you let it go. Then it falls down, it hits the ground at some later time. We could call that t final. And this equation for position as a function of time becomes y of t is h minus 1/2 gt squared. There's no y0, well, y0 is h. But there's no v0 because I dropped it from rest. So I dropped it with 0 velocity. So that term v0 times t is just 0. And then I have plus 1/2 at squared. But the acceleration here is negative. Positive means upward in the direction of y. But the acceleration is downward towards the center of the Earth or towards the ground. So in this case, the acceleration will be a negative value. It'll be negative g. So y is h minus 1/2 gt squared. And if you want to know what's t final, well, t final is when y is equal to 0. It starts at y equals h, it descends until it hits the ground. Well, that's the point y equals 0. So if you set y equals 0, then you see h minus 1/2 gt squared is equal to 0, or h is equal to 1/2 gt squared. multiply both sides of the equation by 2, divide by g, take the square root. T is the square root of 2h over g. We'll see some examples of that in a few minutes. Now, the acceleration due to gravity, g, can be measured at any point on the Earth. And it's almost exactly the same at every point on the Earth. Not exactly. Some places g is a little bit higher than the average. Some places g is a little bit lower than the average. But for the most part, we can just approximate g by the average of all those measurements. G is pretty much the same anywhere on the surface of the Earth. And it was, again, the great Galileo Galilei who determined that G will be the same for all objects. In other words, G is the same for a large massive object as it is for a small lightweight object. You know the story of Galileo and the Leaning Tower of Pisa, where he dropped different objects from the Leaning Tower of Pisa with different weights, and they all hit the ground at exactly the same time, or very nearly the same time. There can be a small difference because of the effect of aerodynamic forces, but if we just think of gravity and ignore aerodynamics, or drop objects like, I don't know, stones, which wouldn't have much of an aerodynamic force, all objects descend with the same acceleration g. And that value we'll take always in this course to be 9.81 meters per second squared. It can be a little different at different points around the surface of the Earth, but 9.81 is a good approximate value anywhere on the surface of the Earth. This is all explained in video on the YouTube channel. So on the YouTube channel where I put the recordings of the Zoom messages, I also put videos which provide a little introduction to each chapter. They're not supposed to replace the chapter. You can't just watch the video and not read the chapter. You have to read the chapter. But the introduction to the chapter will kind of get you started. If you want to be sure you know what equations are important, you can look at the summary page at the end of the chapter. That'll be one page where they give all the important facts from that chapter, and in particular, the important equations. So you can see if the equations you took agree with the equations on the summary page. And like I say, don't use this as your equation sheet for chapter 2. This may not be complete. Take your own notes. Much better for you to take your own notes. Have a physics notebook, which you don't use for anything except physics, or maybe it could be a 3-ring binder. And as you read the chapter, take notes and then put those notes in the binder. You're going to need those equations for the homework problems and for the exams. All right, so take notes in your physics notebook. This is kind of maybe we'll want to have equations and pictures. So here would be a picture for an object moving in one dimension. It's this little sphere moving in one dimension. So it's got a location. Let's say that's the location of the center of the sphere, which varies in time as the sphere moves. Maybe it's moving to the right, so it would have some velocity. But the velocity can change if it's accelerating, if it's speeding up or slowing down. If it's moving to the right, it has a positive velocity because the x-axis we take to be pointing to the right. So the velocity here would be positive. If it's speeding up, the acceleration would be positive. If it's slowing down, the acceleration would be negative, because the rate of change of the velocity would be negative if the velocity is decreasing. Then, of course, the velocity could be moving to the left. In that case, the velocity would be negative. So you see, it's not so simple. Velocity can be positive or negative. Acceleration can also be positive or negative. You know, if x is moving to the left and slowing down, then its acceleration is to the right. And we have these three equations. Make sure you write these down in your notebook. The three equations when acceleration is constant. And be sure you understand the delta notation. Delta Q, where Q is some variable, means a change of Q. It's the final value minus the initial value during which this change occurs. So Q starts out with some value, that's Q initial. It changes. At the end of some time, it has another value, Q final. And Q final minus Q initial is the change of Q. And then delta Q over delta T is the rate of change of Q. All right, so chapter 2 has 5 sections. And, write down the important equations for each of those 5 sections. You can use a page of equations front and back during the exam, and you're going to need it for the homework anyway. Now, we want to look at some homework problems. We want to look at some, of course, there are hints for all the homework problems, but not all of them. There are hints for a lot of the homework problems, but there are not hints for a few of the problems. So at the Zoom meeting, we'll go over a couple of problems that don't have hints. And this will provide you with hints for those problems which don't already have hints. So here's a problem on the assignment called Coosbane. And the statement of the problem is, on the planet Coosbane, if a pebble is dropped from a height h, it falls to the surface in a time t. And the question is, what is the time? Now you have to have some information. So here's the information which is given for one student in the class, namely me. Let's say the acceleration is 4.10 meters per second squared. Acceleration is not a number. Acceleration is a number with a unit. If you don't have the unit, you don't know what you're talking about. And let's say it's 4.10 meters per second squared. Compared to the Earth, let's say. On the planet Earth, the acceleration is 9.81 meters per second squared. But let's say that some astronaut has traveled to a different planet, Coosbane, where the acceleration is lower. Gravity is weaker. And let's suppose the astronaut drops a pebble from a height of 4.9 meters. So he's standing on the top of he's standing at 4.9 meters high. So he's standing at the top of his rocket ship. And he drops an object from that point. It falls straight down and hits the ground. What's the time? In fact, if he didn't know the acceleration, he could measure the time, and from that information, determine the acceleration. This would be the way for the astronaut on a new planet to measure the acceleration due to gravity on that planet, measure the force of gravity on that planet. Well, we're not ready for forces yet, but acceleration anyway. So how are we going to solve this problem? Well, we solve all problems pretty much in the same way. There's a very effective standard way to solve physics problems. It's 4 steps. Step 1, you draw a picture and label it. Label it with letters that stand for the variables that are important. Step 2 is to write down the relevant equations. Now, if you've read the book and taken notes, then you have a page of equations and you can use the equation that you have written down in your notebook. Step 3 is to analyze or solve the equations. You have a bunch of equations, you're trying to calculate something. Some things you already know. There's something you don't already know, and you're trying to figure it out. We're going to use these equations to figure out the thing you don't already know. That takes algebra. So this is where you use algebra. Now, algebra is a prerequisite for this course, so you already have a knowledge of algebra. Finally, you want to calculate a numerical value. So now you need a calculator. You don't even pick up your calculator until you've solved the equations and written down the formula for the quantity that you're supposed to answer. The very last step is to pick up your calculator and put in the numbers. And one of the things that students do wrong, some students do wrong when they start a course like this, is they start by punching numbers into the calculator. No, don't punch numbers into the calculator until you've done the analysis. So let's see how we would apply this method, 4-step method, to this problem. Draw a picture and label it. Well, we're going to have here vertical motion. So let's use a vertical coordinate. We usually call horizontal coordinates X and vertical coordinates Y. So in this problem, we'll have a Y-axis. Y-axis is a number line. Someplace there's the number 0. Let's take the number 0 to be at the surface of the planet, so ground level. So this is the ground on Coosbane. It has Y equals 0. And the astronaut drops the object, this pebble, from a height h. H is 4.90. But I'm not going to write 4.90 on my diagram. I'm going to write h on my diagram. And I've got to keep in mind, h has a known value. But h is the variable. H is the symbol. I mean, somebody else might have a different value of h. You know, if you have a study group with 3 people in the study group, all 3 people might have a different value of h. So you don't want to write down your value, because that wouldn't be your study mate's value. You write down the variable name h for height. Now here's the stone as it's falling down. It was let loose at this height. Now it's falling down. It's partway down. It has a velocity v. And it has an acceleration minus g, because this is free fall. But g is not 9.81. That would be on the surface of the Earth. This is on the surface of Coosbane. So we won't call this minus g. G we always mean for 9.81. Let's call this g sub k for g on Coosbane. Now again, I know the value of g sub k. It's 4.10 meters per second squared. but I'm not going to write down 4.10 meters per second squared because that's a variable. That's something that could be different in different problems. I'll just write it down as a symbol. So this is step one. Step two, write the relevant equations. Well, this is a problem with constant acceleration. I know the equations for constant acceleration. I wrote them down in my notebook. Y at time t is y0 plus v0t plus a half at squared, where t equals 0 is the time when I released the pebble. So this equation corresponds to the time when I released the pebble. T is the time later. All right, now y0 is h. V0 is 0. A is minus gk. So y at time t is h minus 1/2 gt squared. So that's step two, write the relevant equations. You see, I don't have any numbers yet. I just have symbols. The step three is to solve the equations for the unknown. What's the unknown? What's the time? So t is the unknown. So that's the time when it hits the ground. So t corresponds to y equals 0. If y is equal to 0, then 0 is h minus 1/2 gt squared, or I could say h is 1/2 gt squared. And now the unknown is t. So this is analyzing the equations. The analysis was to set y equals 0 and get an equation for t. Now this is an equation for t squared, but I just need to take the square root to get the equation for t. So here's the equation for t. T is the square root of 2h over gk. So that's step three. And now step four is to calculate the number. Plug in the numbers and determine t, because that's what Law and Capital will want you to type into the box. So square root of 2, h was 4.9 meters, g was 4.1 meters per second squared. I always write down the number with its unit, because that'll tell me what the unit is. The unit here, I mean, the answer is going to be a number with a unit. Well, what's the unit? Well, I have here meters divided by meters, so the meters cancel. I have 1 over second squared, so that's the same as second squared. I'm going to take the square root. The square root of second squared is seconds. So the unit is seconds, which of course I should expect because this is a time. And now what about the number? Well, I have here 2 times 4.9 divided by 4.1. It's about 2 times 5 would be 10 divided by 4. 10 divided by 4 would be 2.5. It's the square root of 2.5, which is about 1.5. So the answer is going to be about 1.5 seconds. Now, you'll want to do this more accurately, so you pick up your calculator and calculate this number with your calculator. So that's how we solve these problems, by this 4-step method. The important thing to understand is I never calculated anything until the very last step. Now let's see if there are any questions. I don't see any questions on the chat. Does anybody want to unmute your microphone and speak up a question?
Hi.
Yeah.
So for my version of the problem, it's asking for the height. So should I just stop at step 3?
It's asking for the height.
Yes. Yeah, it gave me the time and the acceleration
Oh, okay.
and asked for height.
So in this version of the problem, it gave you the height and the acceleration, and it asked for the time. But you could have a different version of the problem in which it gives you the height and the acceleration. No, the time and the acceleration, and ask for the height. Well, you would analyze this problem in the same way as you see here. And now, after analyzing the problem, you have this equation. Now, in your version of the problem, you know the acceleration and you know the time. So you would just calculate 1/2 g times time squared. The answer will be a number with a unit. What's the number? Well, g is meters per second squared. And t is seconds. But t is squared, so that will correspond to, that will give you second squared. Now, second squared cancels second squared, and so the unit will be meters. And the number will be 1/2 whatever you have for the acceleration times whatever you have for the time squared. You see, you should never have a problem figuring out the unit. Because, well, of course, you could have guessed, well, it's going to be a height, so it's going to be meters. And if you use standard units, it'll be the standard unit of height, standard length, meters. But you never should have any problem figuring out what the units are, because the calculation tells you what the units are. You just put in the unit for the various quantities in the expression, multiply them together, and you'll get the unit. Now, in this problem, it's very easy, but in other problems, it's not so easy. And students often will write on the discussion board, what's the unit for this problem? Well, you can always get the unit by just looking at the equation that you use to calculate the number. All right, let's look at another problem. One of the problems on the assignment is acceleration of a car. A car on a straight road is stopped at a red light. When the light turns to green, the car accelerates with a constant acceleration. It reaches a speed of 72 kilometers per hour in a distance of 142 meters. And we'll assume that it accelerates for all that time at a constant acceleration. The question is, what's the acceleration of the car? Maybe some people have already done this problem, but let's see. This is a problem for the homework assignment, which is due Monday. Problem set 1. So not everybody has done these problems, but some people have already done some of the problems. Well, if you haven't done the problem, let's see how to do it. We'll use this 4-step method. Step 1, draw a picture and label it. Well, here's the picture. The car is moving on a straight track or a straight road, motion in one dimension. It starts at some position which we could call 0. Its motion is, its velocity is 0 at that time because it's at a red light. Then it accelerates, and at some later time, when its distance is d, it has a velocity v. So there's a picture of the problem. Now, what do we already know? Well, we already know this speed. And this time. of this distance. Says it reaches a speed of 72 kilometers per hour in a distance of 142 meters. But I'm not going to write 142 meters on my diagram because somebody else might have a different number, and d is a variable. It could be different for some other version of the problem. I'll just write down the symbol for distance, d. And eventually I'll use 142 meters. And I know what the velocity is at that point. It's 72 kilometers per hour, but I'm not going to write down here 72 kilometers per hour. That's not even in the right units. I'll just write it down as v. Those two quantities are known. That's one diagram. I might write down another diagram. I might write down a plot of x versus t. This is a case of constant acceleration. So position increases as the square of the time. That's Galileo's square of the time. So the graph of x as a function of time is a parabola in the xt plane. Now, x here is not vertical. In this graph, x is vertical, but x is not vertical. X is along the ground. X is horizontal. T is not a direction. T is time. You know, T doesn't have a direction. It's just time. And I know from Galileo that x will increase as t squared. So the graph will be a parabola. And now what I'm trying to figure out is the acceleration. So I want to know what's a. So that's step one. Now step two, write the relevant equations. Well, this is constant acceleration. So I know the three famous equations for constant acceleration. The third equation is the one I want. It's the equation that relates speed and distance. That equation, delta v squared, is 2a delta x. That was the third of those three equations for constant acceleration. Now, a is the unknown, but I know delta v squared. It starts with v equals 0. It ends with v equals v. So delta v squared is the same as v squared. It's the final value squared minus the initial value squared. Vf squared minus v0 squared. That's delta v squared. And that's 2a. A I don't know. A is what I'm trying to figure out. Delta x, well, how much is position changed? By d, you know? It's the final x, which is d, minus the initial x, which is 0. Or it's just the change in x. X goes from 0 to d, the change in x is d. So I put in here d. And now I use a little bit of algebra. I solve for the unknown. Just divide both sides of the equation by 2d. Now I can actually simplify this a little bit because v0 is 0. It started at a red light where it was not moving. So I just have vf squared is 2ad. So a is vf squared over 2d. So that's step 3. And now I calculate the number. I put in for VF 72 kilometers per hour, but I better convert that to standard units. And I put in for D 142 meters. So I have 72 kilometers. A kilometer is 1,000 meters divided by 1 hour. Kilometers per hour. An hour is 3,600 seconds. So to travel a kilometer, it would take 3,600 seconds. So this is its speed. This is its unit. 72 kilometers per hour. But I've converted the length to meters and the time to seconds, so that I'll get a standard unit as the answer. Now, the answer is going to be a number with a unit. So what's the unit? Well, meters squared divided by seconds squared divided by meters. So here's meters squared divided by seconds squared divided by meters. Now I can cancel 1 power of meters. Meters squared divided by meters is just meters. So it'll be meters divided by seconds squared. So you see, I don't have to know what the unit is. The calculation will tell me what the unit is. Now, of course, that's the appropriate unit for an acceleration, because acceleration is length over time squared. So it should be meters divided by seconds squared. Sure enough, it is. Now I have to calculate the number. Now, this number is 72 over 36 is about 2. 2 squared is 4. Here's 1,000 over 100, so that's 10. Squared is 100. So it's about 400 in the numerator. Here's about 280 in the denominator. I can cancel 1 power of 10. It's like 40 over 28. I can divide both upstairs and downstairs by 4. So it's 10 over 7, roughly. So it's roughly 10 divided by 7 would be 14. No. 10, let's see. If I cancel these, let me change if I divide this by 4, I get 100, and I can cancel 1 power of 0. I would have 10 here. I cancel 1 power of 10. If you divide this by 4, that'll be 7. Now what's 10 divided by 7? 1.4. So acceleration is 1.4 meters per second squared. Now you'll want to do this with a calculator. I mean, I can sort of do it in my head, just doing the arithmetic in my head, but you're going to be better off just using a calculator. Divide 400 by 280. It's not exactly 1.4, but it'll be close to 1.4. This is approximate. 14 wouldn't be sensible, because 14 meters per second squared is more than a G. G is only 9.8 meters per second squared. So that would be larger than a G. Well, you're not going to accelerate your car at more than 1 G. It'd be a little fraction of a G. Did you see the fourth step, putting in the numbers, is the very last thing you do. Somebody wrote a question on the meeting chat. Are the problems posted on Lon Kappa not the corresponding quiz questions? No, it's not the quiz questions. It's the problem set. These are questions from problem set 1. That's the problem set which is due, I guess it's due, what did we say? Problem set is due Monday. We're here on the 8th. Problem set is due on the 11th. The quiz is already due. Well, it's due at the end of tonight. The quiz questions are different than the problem set questions. The problem set questions are usually numerical problems like this. Quiz questions are usually just multiple choice questions. And if you've read the chapter, you can usually answer those multiple choice questions in a minute or two. You read the question, might take 3 minutes to read the question. You know the answer because you read the chapter. So it might take 3 minutes to answer the question. And you don't have to do any calculation. Well, sometimes you do, but not a long calculation. All you have to do is hit the button for that multiple choice. So the reading quiz is not not supposed to take very long. After you read the chapter, it should take maybe a half an hour to an hour. But the problem set is different. The problem set is questions like these, where you have to do calculations. You have to, what does it take to solve these problems? Well, you have to draw a picture. You have to write down the relevant equations. Hopefully you've already got those written on your equation sheet, so you don't have to search back through the chapter to find the right equation. You have to solve the equations. You have to apply algebra. Finally, you have to calculate a number. So that's not going to take a minute or two. That could take 10 or 15 minutes to do all of that. So the problem set is expected to take several hours, maybe 5 hours, maybe 8 hours. So don't leave the problems till the last minute, because it's going to take you a number of hours to do those problems. Don't do them all at one time. Do a few each day and finish them up on the day that they're due. But by the time you come around to Monday, you should have done most of them. You're just finishing up. I believe these 3 problems are problems on that problem set, which is due Monday. And now let's do one more. Passing on a highway. I suppose most of you have a driver's license and you've passed on a highway. On a straight road, one car is traveling at a constant speed v1 in the slow lane. So that's the red car. Okay. A second car has speed v1 in the left lane, but he wants to go faster. He's in the fast lane. So the driver of the second car decides to pass the first car. So he applies the accelerator. When you apply the accelerator, you accelerate. You go faster. So when he's 20 meters behind the first car, he can see the first car is not going fast enough, and he wants to go faster, so he's going to accelerate. He'll accelerate, and we'll assume that the acceleration is constant a. And the question is, how far will the second car travel before it passes the first car? Now, of course, cars have some length, so we'll calculate the distance he has to travel before he's just starting to pass the first car. In other words, when his front bumper has reached the same position as the red car's rear bumper, how far has the blue car traveled? Now, again, it's a 4-step process. First, you draw a picture. Now, this picture is given in the problem. You may not want to draw that again. This picture doesn't really show you what you need to know. This is actually 2 pictures. Here's the picture where the blue car is starting to accelerate. Here is the picture where the blue car just reaches the red car. So these correspond to 2 different times. So this isn't a very good picture. A better picture would be to draw the positions as a function of time. So you can make a graph of position as a function of time. There are 2 cars, so there'll be 2 graphs. There'll be a graph for the red car. The red car starts out at 20 meters. We'll take this to be 0. So I'll take this to be 0. The red car is at 20. And I'll call that number D, because I want to write the equations not in terms of numbers, not in terms of variables, but in terms of symbols. So I'll call that D. And then the red car just continues traveling along with the same velocity, v1. So the graph is a straight line with slope equal to v1. v1 is given. That's the speed of the red car. 25.8 meters per second. But I'm not going to write 25.8 meters per second squared here. I'm going to write V1 here is the slope. And this graph is x1 as a function of time. It's a straight line because the slope is constant. Slope of position as a function of time is the rate of change of position with respect to time. That's velocity. Now, how about the blue car? Well, the blue car starts out with the same slope. So if the blue car didn't apply the accelerator, the blue car would travel along this line. This would be the motion of the blue car if he didn't apply the accelerator, because he'd just continue to travel 20 meters behind the red car. But he wants to pass the red car, so he applies the accelerator. So initially, his velocity is the same, v1, but then it speeds up. And at some point, namely the point I'm looking for, he'll pass the red car. In other words, his position will be larger than the position of the red car. So this is the time, t1, when he passes the red car. So there's the picture. And I've even sort of analyzed what's going on just by using the picture. Step 2 is to write the equations. Well, I can write the equation for the position of the red car. X of t is d plus v1t. And I can write down the coordinate for the blue car as a function of time. It's v1t plus 1/2 at squared. This is the equation for constant velocity starting from point D with velocity v1. This is the position or coordinate as a function of time for a car that starts with velocity v1 at time 0, and then it accelerates with acceleration a. Now, when the pass starts is when x red is equal to x blue. So he just begins to pass the red car when x2 is equal to x1. So let's write down x1, it'd be d plus v1t1 equals x2, would be v1t1 plus 1/2 at1 squared. So that's x red at t1 is equal to x blue at t1. That's what I'm looking for, t1. No, that's not what I'm looking for. What I'm looking for is the distance. So this distance is the answer. It says, how far does the second car travel when it begins to pass the first car? Well, it traveled from 0 up to this point where the two are at the same position. So that's the answer I have to calculate. But, this is an equation where the only unknown is T1. See, D is 20. V1 is 25.8. A is 2.5. So in this equation, the only unknown is T, T1. So the algebra comes in determining T1, but that's not quite the answer. The answer is this distance at that time. So here's where the algebra comes in. See, the algebra is fairly simple because it's a quadratic equation, but it's a simple kind of quadratic equation because on the left-hand side, I have V1, T1. On the right-hand side, I have V1, T1. I can cancel that on both sides of the equation. I just have D is 1/2 AT1 squared. So the answer is, how far did the blue car travel at the time T1? Well, it's this distance, or equivalently, it's this distance. It's D plus V1 times T. Cancel these two equations, solve for T. T is 2D over A square root. So here's the algebra. That's the distance that the blue car traveled. The distance that the red car traveled was just V1 times the square root of 2D over A. Now I pick up my calculator. So D is 20. V1 is, well, it's about 26, let's say. Square root of 2 times D, D was 20, so 40 divided by A is 2.5, and the unit is meters. The unit had better be meters because I'm calculating a distance. And it is meters because D has units of meters. V times T has units meters per second times seconds, so that's meters. So indeed, it is meters. And, you need a calculator now to calculate the number, let's say something like 120 meters. Well, I've already used an hour. I try to limit these Zoom meetings to an hour. Does anybody have a question on the chat? No. Anybody want to unmute your microphone and speak up? This problem has a hint on the hint in the hint folder. So I think the hint folder has this picture in it. But at the Zoom meeting, I can actually go over a little bit of the reasons and can give a little more detail. So that problem set corresponding to one-dimensional kinematics is due Monday. You should have a study group. Meet some other students in the class. Maybe you know some other students in the class. Maybe they're living in the same dorm or something like that, or they have the same major. Set up a study group and discuss the problems with other students. And if you get stuck on a problem and you don't know how to proceed, formulate a question and write the question on the discussion board. Hopefully somebody will answer your question and get you unstuck. So I've already used up more than an hour. I think I'll end the meeting. Let me start by ending the recording.